Okay, hey Algebra 2 students, now we're going to look at the definition of what a radical is and kind of explore some of the big idea rules of radicals. Similar to how we made an exponent rule chart, we're going to just make a nice organized rule chart for our radicals. So feel free to print this out if you would like to, or to do it in your notebook, whatever is easiest. And this is also chapter R. I believe it is chapter R.6. So that is in the review chapter of the textbook, but we are touching on it now because it was a good timing in the calendar. So the first thing we're going to look at is radicals. So I'm going to kind of flip down here to the third row, and I'm going to look at the square root of 20 times the square root of 5. That's something that we've seen before in geometry. So the rule is that you can say that that is equal to the square root of 20 plus 5. Right, I can put those together. So breaking apart radicals or square roots, remember it has to be two things that multiply to be that number. So 20 and 5 work because they multiply to be 100. But what's really nice is the square root of 100 is just 10 because it's asking what times itself gives you 100, and that is 10. So the general rule is that the square root of a times the square root of b is the same thing as the square root of ab, or a times b. Right, you can go backwards and forwards. We generally, in geometry, went the other way, right, going from the square root of a number and breaking it apart, but you can go both directions. We're also going to look at what happens when we do the square root of 300 over the square root of 3. So similar to how you can break them apart with multiplication, you can also put them back together, right, with division as well. So I can say that this is equal to this. You can also confirm this in your calculator. If you do the square root of 300 and the square root of 3 and divide them, it should be the same as the square root of 300 divided by 3, which is the square root of 100, which is going to give you a 10. So this one is really similar. The orange one I would call like a product rule, right, if you want kind of a name. This would be more of a quotient rule. And in fact, both of the bottom two are both quotient ideas. So this one is kind of written out like so. Okay, so you can put them together or break them apart. The bottom one is kind of the reverse of this quotient rule. So this bottom one kind of goes the other way. Right, the bottom one is really the same thing. It's the idea that the square root of 4 over the square root of 9, or excuse me, over 9. You can call it the square root of 4 over the square root of 9, which is going to be 2 over 3. So this one is written in this fashion and says that you can break it up going backwards. So this is really the same rule, just reversed. Same thing, you can also confirm by doing it on your calculator. The square root of 4/9 is the same as square rooting both of them separately. So the middle one, right, this one was one that you guys explored a lot in geometry. And the bottom two are kind of intuitive based on what we're seeing with the first rule that you guys refer back to in geometry a lot of times with the product rule. So remember, for the bottom two quotient ideas, you can confirm those using your calculator if you want to kind of double check, or if you want something to solidify that reasoning why. And then at the top, what I've got is another idea, and this one's going to be a little bit newer, so that's why I kind of wanted to start with what you were more familiar with. So if I take 25 to the 1/2 times 25 to the 1/2, now my exponent rules say that if I have the same base raised to a power, right, I can add the exponents. So I could say that that's 25 the 1/2 plus 1/2, which is 25 to the first power. And that's just 25. So the question is, what number times itself, right, these are the same things twice, what number times itself gives me 25? Right, the number is 5. So somehow 25 to the 1/2 power is the same thing as 5. And isn't that the same thing as like the square root of 25, right? Square root of 25. So these are actually all synonymous, which is kind of cool. So the general rule is that if I have a number raised to the 1/2 power, that's the same thing as the square root of the number, which is a really weird but kind of interesting thing. So it's saying like 25 to the 1/2 power is the same thing as the square root of 25 or 5. And you can kind of see that really nicely in our example. Similarly, if I do 27 to the 1/3 times 27 to the 1/3 and so on, I could say that that's the same thing as 27 to the 1/3 plus 1/3 plus 1/3. That's 27 to the first power, right? Or 3 over 3, if you want to do kind of an intermediate step. So what number times itself, right? A number times itself, that gives me 27. Well, isn't that just 3? Right? Or the cube root of 27. So the same thing applies, right? You can think about this as 3 times 3 times 3. Cube root of 27 times the cube root of 27, right? We need 3 of them rather than 2 due to cubing compared to squaring. So a to the 1/3, same thing as the cube root of a. These rules go together, and generically, if you want like a more general, a to the 1 over nth power is the same thing as the nth root of a, right? The square root, the cubed root, the fourth root, all that kind of stuff. The interesting thing is the square root, we don't put a 2 there, but you could if you wanted to have that consistency built into it. And then continuing on to our next page, I've got a couple of practice problems, just practice going forwards and backwards with this idea that we've just done, right? The idea that a to the 1 over n is the nth root of a. The example that we could look at is 1/2, right? That's a really helpful one for people to think about. So the top one, number 3, asks you to start with the powers and go to the radicals. So this one is asking you to go from powers to radicals, right? To go the other way. And then this one is asking you to go from radicals to powers or exponents, right? You can kind of see that in the directions. So why don't you pause the video and try and do these with what we have just seen, and then unpause when you're ready to check. Okay, so at this point you've unpaused the video. Sorry about my recording, it's not letting me pause, it's just continuing to record, don't know why. So I could not pause and fill them in. 36 to the 1/2 power, that's the same thing as the square root of 36. What times itself is 36? That's going to be a 6. Now this one is, B, is the same thing, except for, remember if we have a negative exponent, like if you have x to the negative 2nd power, we want to write that as 1 over x squared. So the 36 to the negative 1/2, that's 1 over 36 to the 1/2, or 1 over the square root of 36, which ends up being 1/6. So this is keeping in mind some of those exponent ideas, and that's why we wanted to start with exponent ideas, because they are very foundational to our radical ideas. Okay, continuing on, part C is 36 to the 3 over 2. That's kind of weird. What if I wrote that as 36 to the 1/2? All just being cubed, right? Instead of doing the 3 times the 1/2, which is 3/2, let's just kind of keep it off to the side. So this one, it's going to be the same thing as the square root of 36. And it looks like that cubed, all that cubed is doing is just going to be cubing it at the end. So it's going to become 6 cubed. And so it's going to be a 36 times a 6. Let's see what that is. Looks like 216. Sorry for the pen, it's not looking like a cubed. Okay, so just practice going back and forth between like to the 1/2 power and square rooting. Number 4 asks us to go the other way, so I'll just kind of leave this up here for reference. So if I have the 7th root of y, I could write that as 1090 y to the 1/7, right? There's not really as much simplifying that happens here. For part B, I've got the square root. You don't really have to write the 2 there, but you can. That's like 4y to the 1/2 power, right? Just kind of practicing going back and forth. The top one was more useful for simplifying. This one, we can't really break it down so much. If you wanted to, you could think about the square root of 4 as 2 and write that as 2 times y to the 1/2. That would also be an acceptable answer as well. Okay, and then these are some problems that we're going to start now, and we'll probably touch back on these during class. So these are some practice problems. I've got two D's. I guess it should be E and F. Letter E and F are definitely the more complex ones that we're going to look at together. But A, B, C, and D might be a little bit more approachable now with what we've practiced. So you're going to simplify and assume that there's no weirdness with negative signs. What that means up here, we're assuming like if I say the square root of x squared, you can just tell me x. The tricky thing is it could be like if I do a -5 squared and then square root it, right, I get 25, positive 25, being square rooted, which is 5. So notice sometimes it's not the original x, it's like the absolute value of that -5. So sometimes you get weird stuff like that. We're just assuming, don't let the weird stuff happen. So we're assuming, right, not this, we're assuming that the square root of x squared is x. We're assuming that there's no funny business with negative signs. So kind of put that off of your mind. So if we go ahead and start these, the first two are probably more approachable. All right, I want to break this down into two things that multiply to be 250, and I'm looking for perfect squares. I know that 25 times 100, or times 10, excuse me, not 100. 25 times 10 is 250, and 25 is a perfect square. The square root of 25 is going to be a 5. So my final answer, this is how you simplify radicals, is 5 square root of 10. And this is how I would expect you to simplify. This is also how you're going to be expected to simplify further on in math. So it's a good idea to write it like this rather than jumping to a decimal form. This one's kind of that division rule, and I can't break down a 32 or a 2. So what if I put them together, right? It says that I can put them together or pull them apart. 32 cut in half is 16, and the square root of 16 is 4. So generally you want to just change it into a different form. If the form you have isn't doing anything, try and change it up. Okay, and then the square root of 8x cubed. So I like to think of this as the square root of 8 times the square root of x cubed. And these four are going to be ones that we'll talk about tomorrow. So let's just try and kind of look at C, and maybe we'll look at D, E, and F tomorrow during class. So if I look at the square root of 8 separate from here, the square root of 8, I would want to break it up into two things that multiply to be 8, and one being a perfect square. So 4 and 2 sounds good. For the second bit, the x cubed, I want to break it up into something that I can square root, and I know the square root of x squared, right? What times what is x squared? It's x. So I'm going to break it up like this into two things that multiply to be x cubed. And then I'm going to simplify each of these. And we will definitely be talking about this tomorrow. And so at this point, this is all you can do. So I would generally ask the standard way to write it is 2x times the square root of 2x, right? Where anything that's stuck underneath the square root just stays there. And then anything you could have square rooted gets kind of lumped together. So notice that these two things are kind of becoming that. So we're going to look at these tomorrow, at how we break them down. But generally you want to look for things that you can square root. So you break up the x's just like you break up the numbers, right? We can also look at D real quick too. So I would break up this as the square root of 36 and the square root of x squared. Oop, and 6 times 6 is 36, and x times x is x squared. So this one, both of them happen to be square rootable. Part C was actually harder. I should have flip-flopped those for you guys. And part C was more difficult because you had to break down the x cubed. Generally, you want to look for an even thing, or an even, not a thing, an even exponent, right? Like the square root of x to the 4th power is x squared. And that's because x squared times x squared is x to the 4th. So it doesn't always have to be an exponent of 2, but you can break it up that way if you like. Right, you also could have broken it up into 2x squareds and then just said x and x. So we are going to look at part E and part F tomorrow together, as those I think will be a good conversation for us to do as a team.